Welcome back to another strategy session. If you're a focused learner aiming to truly master your Cambridge Additional Mathematics exam, specifically the 0606 syllabus, you are in exactly the right place. Today, we're taking a sharp, no-nonsense look at coordinate geometry. But we're not just going to mindlessly memorize formulas. No, we are going to bridge the gap between the abstract math of the circle and the tangible, real-world technologies you use every single day. We're going to crack open the mechanical blueprints of the geometric shapes that quite literally map our world. And most importantly, we're going to show you how to tailor your exam answers to fit the question perfectly. No loose threads. Let's get started.
Okay, let's dive into this. Take a look at this simple, everyday scenario. A mobile phone using a mapping app to navigate. We rely on this constantly, right? But have you ever actually stopped to think about the coordinate geometry making it happen? To find your precise location, your phone uses the Global Positioning System, or GPS. Basically, your phone's receiver is constantly communicating with satellites orbiting the Earth. It knows exactly where those satellites are, and it calculates its distance from them. But the math that translates that distance into that little blue dot on your screen, well, that relies entirely on the geometry of circles. So, pose yourself this question. How does your phone actually know exactly where you are? Think about it. If your phone connects to just one satellite and knows it's a certain distance, let's call it r, away from it, that doesn't give you a location at all. It just tells you that you are somewhere on the circumference of a giant circle with radius r. You could literally be anywhere on that ring. That's why one or even two satellites just aren't enough. You need multiple intersecting circles to pinpoint a single precise location. This mathematical concept is called trilateration, and it's the foundational reality of why we study circles on a coordinate plane.
And this brilliantly illustrates a concept recognized centuries ago. Listen to this quote from Isaac Newton. "The description of right lines and circles upon which geometry is founded belongs to mechanics." Geometry isn't just about casually drawing these shapes, it's about the mechanics of how they operate, how they intersect, and the strict rules they follow. Newton understood that lines and circles are the mechanical blueprints of our universe. Now, before we continue to unpack the blueprint of a circle, subscribe to our YouTube channel, Ace the Exams, at ACExams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Okay, let's look at the math.
Section 1. Anatomy of a circle. Let's look at the standard equation. We need to break down the fundamental algebra that makes those GPS circles entirely possible.
Right, here is your absolute foundation, the standard equation of a circle. It looks like this: x minus a all squared plus y minus b all squared equals r squared. But when you look at this in an exam, don't just see letters. I need you to see the mechanics. A circle is simply the locus of all points, which we call xy, that are a fixed distance away from a center point. That center is AB, and the fixed distance is the radius r. What's so beautiful here is that this formula, it's derived straight from Pythagoras' theorem. You're essentially just mapping out a right-angled triangle where the hypotenuse is always your radius.
Now, what's really interesting here is seeing how that standard equation can be disguised by examiners. On the left, we have our standard form, where the center and radius are super obvious. But if you multiply out those brackets, you get the expanded form on the right, x squared plus y squared plus 2gx plus 2fy plus c equals 0. Look, we often see students like Alex overload their answers with raw math facts here without analyzing the equation, or a student like Sam who just rushes and misses what's in front of him. It looks intimidating, but it's the exact same shape. The clever trick is that even when it's multiplied out, you can still easily extract the center and radius. In this expanded form, your center is just negative g, negative f, and your radius is the square root of g squared plus f squared minus c. It's a perfect algebraic Dakota ring.
Section 2. Lines and circles. Points of intersection. Let's see how this builds when we introduce a totally new element, a straight line on that same coordinate plane.
Stop scrolling, subscribe to our YouTube channel, Ace the Exams, at AceTheExams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 great boundaries. Join them right now by subscribing to at AceTheExams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions. Okay, back to it. When a line meets a circle, we face 3 geometric realities. The line can slice right through the circle, crossing at 2 points. It can graze the edge, touching at exactly 1 point, or it can miss the circle entirely. To figure out which scenario we have, we substitute the line's equation into the circle's equation, creating a quadratic. And here is where we use the discriminant rule of 3. By calculating the discriminant b squared minus 4ac, we can perfectly predict the geometry. Greater than 0, 2 real roots, so 2 points of intersection. Exactly 0, 1 repeated root, so it touches at 1 point. Less than 0, no real roots, meaning it misses completely. Pure algebra predicting pure geometry.
That specific scenario where the discriminant is exactly 0 brings us to a highly specialized and very frequently tested feature. Section 3. The power of tangents. A tangent is a straight line that touches the circle at exactly one single point, and it follows a golden rule you absolutely must remember for your exams. A radius drawn from the center of the circle to that exact point of contact will always, without fail, be perfectly perpendicular to the tangent. This means they meet at exactly 90 degrees. Algebraically, this gives you incredible power. If you know the gradient, or slope, of the radius, let's call it m1, you instantly know the gradient of the tangent, m2, because for perpendicular lines, m1 multiplied by m2 always equals -1. If the radius has a slope of 2, the tangent has a slope of -1/2. It's an immediate, powerful mathematical shortcut.
Section 4. When circles meet. Let's bring the theory full circle and reconnect right back to our original GPS trilateration concept. When two circles intersect at two distinct points, they share a line connecting those points. We call this a common chord. Finding the equation of that line sounds like an absolute nightmare of quadratic algebra, but actually there is a brilliant shortcut. Step 1. Write both circle equations out in their expanded form. Step 2. Simply subtract one equation from the other. Why? Because both start with a single x squared and a single y squared, so the squared terms completely cancel each other out. Step 3. You are instantly left with a simple linear equation, no squared terms at all. That resulting equation is the exact line of the common chord. It's an incredibly elegant trick to solve a complex problem fast.
But hey, what if the command word in the question just asks you to determine if or how the circles meet, without needing the exact coordinates? You don't need quadratics at all for that. You just analyze the centers and radii. If you calculate the distance between the two centers, we'll call that d, you can compare it directly to the radii, r1 and r2. If the sum of the radii perfectly equals d, the circles touch exactly once on their outside edges. If the difference between the radii equals d, they touch internally. If r1 plus r2 is less than d, they're completely separate. And if the difference is greater than d, one is entirely inside the other. Simple distance calculations reveal the complete geometric relationship. This is how top students save time.
As we wrap up this explainer, let's take a step back and look at our complete mathematical system. Section 5. The big picture. We've covered a ton of ground today, from phone apps to standard equations and quadratic discriminants. So, the crucial takeaway for your exam strategy is this. Everything we've discussed highlights how visual physical geometry has a clean, simple algebraic test. Want to know if a straight line hits a circle? Don't waste time drawing it, just run the algebraic discriminant test. Want to know how two circles relate to one another in space? Just use the radii distance test. The geometry gives us the physical context, but the algebra gives us the absolute, undeniable proof. Now listen, students who implement these mathematics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. We started today by looking at how your phone maps the world using trilateration. You now have the exact mechanical blueprints and algebraic tools that make that possible. So I'll leave you with this final thought. With these tools securely in your mental toolkit, how will you use intersecting circles in programming, mapping, or engineering tomorrow? The math is no longer abstract. It's waiting to be applied. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGSC to excel in your Cambridge examinations. Subscribe right now to acetheexams_IGSC and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for mathematics and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams, your Cambridge success starts here.